What's up? I'm Jaco. Today we're diving into unsupervised learning. This is where the algorithm has zero labels, no right answers, no target variable. It just looks at raw data and finds patterns on its own. We'll cover clustering, dimensionality reduction, and anomaly detection. 5 algorithms you'll use constantly in real projects. Practice everything on dataforall.dev, link in the description. Let's go. Here's the roadmap. 5 sections that build on each other. First, k-means clustering, the most popular algorithm for grouping data. Then how to evaluate clusters when you have no labels to compare against. Third, hierarchical clustering, a completely different approach that builds a tree of clusters. Fourth, PCA and dimensionality reduction, how to compress your data while keeping the important stuff. And finally, anomaly detection, finding the data points that don't belong. So what makes unsupervised learning different? In supervised learning, you have labels. You know the answer. The model learns to predict that answer. In unsupervised learning, there are no labels at all. The algorithm looks at your data and finds structure by itself. It discovers hidden groups. It reduces complexity. It identifies outliers. The 3 main techniques are clustering, dimensionality reduction, and anomaly detection. And the cool part is, you don't need labeled data, which is great because in the real world, most data is unlabeled. K-means is the most common clustering algorithm. Here's how it works. You pick a number k, that's how many groups you want. The algorithm places k random centroids in your data space. Then it assigns every data point to the nearest centroid. After that, it recalculates each centroid as the average of all points assigned to it. Then it reassigns points again, and it keeps repeating until the centroids stop moving. That's convergence. It's simple, it's fast, and it works great when your clusters are roughly spherical and well separated. The big question with k-means is how do you choose k? That's where inertia comes in. Inertia measures the sum of squared distances from each point to its centroid. Lower inertia means tighter clusters. If k equals 1, inertia is huge. If k equals n, 1 cluster per point, inertia is 0. The elbow method plots inertia against k. You look for the point where adding more clusters stops helping much. That bend in the curve is the elbow. That's your sweet spot for k. How do you know your clusters are actually good when you have no ground truth labels? The silhouette score measures how similar a point is to its own cluster versus the nearest other cluster. Range is -1 to +1. Higher is better, but don't rely on a single metric. Combine the elbow method with silhouette scores. Plot your data in 2D using PCA and visually inspect the clusters. Separated compact groups mean good clustering. Overlapping groups mean revisit your K and try different methods. Run K means DB scan and hierarchical, compare them. Let's break down the silhouette score formula. For each point I, you compute A of I, the average distance to other points in the same cluster. Then B of I, the average distance to points in the nearest neighboring cluster. The silhouette score is B minus A divided by the max of A and B. A score of +1 means the point is far from neighbors and close to its own cluster. Perfect assignment. 0 means the point sits right on the boundary between 2 clusters. And -1 means the point is closer to a neighboring cluster. It's probably misclassified. Hierarchical clustering takes a completely different approach. You don't need to pick k up front. The agglomerative method starts with every point as its own cluster. Then it merges the 2 closest clusters. Repeats. Keeps merging until everything is one big cluster. The full history is captured in a tree called a dendrogram. To get your final clusters, you cut the dendrogram at a chosen height. The number of vertical lines your cut crosses equals the number of clusters. This gives you flexibility to explore different values of k after the algorithm runs. When merging clusters, you need a way to measure distance between them. That's what linkage methods define. Single linkage uses the minimum distance between any 2 points in the clusters. This creates chain-like elongated clusters. Complete linkage uses the maximum distance. This creates compact round clusters. Average linkage takes the mean of all pairwise distances, a balanced middle ground. And Ward linkage minimizes the increase in within-cluster variance at each merge. Ward is the most popular choice because it tends to produce evenly sized clusters. Reading a dendrogram is straightforward. The y-axis shows distance. Tall branches mean well-separated clusters. Short merges mean very similar data points. The x-axis shows your samples as leaf nodes. Draw a horizontal line at any height and count how many vertical branches it crosses. That's your number of clusters. Now k means versus hierarchical. K means is faster and scales better, but you must choose k up front. Hierarchical is slower, but gives you the full tree. You can explore different k values without rerunning. Use k-means for large datasets. Hierarchical for smaller ones where you want to explore structure. PCA stands for Principal Component Analysis. It compresses your data while preserving the most important patterns. Here's the process. First, standardize your features so no single variable dominates. Then, PCA finds new axes called principal components. These are the directions of maximum variance in your data. You select the top K components that explain around 95% of the total variance. Then project your data onto those components. You go from D dimensions down to K, less noise, fewer features, and the key information is still there. Each principal component captures a certain amount of variance. The eigenvalue tells you how much. The variance ratio is the fraction of total variance that one component explains. All ratios sum to 1. You plot the cumulative sum and look for the threshold, usually 90 to 95%. That's how many components you keep. This is called a scree plot. It looks a lot like the elbow method. The first few components capture most of the variance. After that, you get diminishing returns. Everything below the threshold is mostly noise. When should you use PCA in practice? Visualization. Reduce to 2D or 3D so you can actually plot your data and see the clusters. Pre-processing. Remove noise before feeding data into ML models. Your model trains faster and often performs better. Compression. Store high-dimensional data more efficiently. Feature engineering. PCA creates uncorrelated features which many algorithms prefer. Exploratory analysis. Discover hidden structure you didn't know existed. And noise reduction. Low-variance components are mostly noise. Dropping them cleans your data. Anomaly detection finds data points that don't belong. This is critical for fraud detection, system monitoring, quality control, and cybersecurity. There are 3 types of anomalies. Point anomalies, a single outlier, like a $50,000 transaction on a $500 account. Contextual anomalies, normal in one context but abnormal in another, like 80-degree weather in summer versus winter. And collective anomalies, a group of points that are anomalous together but individually look fine, like a sequence of failed login attempts. Isolation forest is the go-to algorithm for anomaly detection. The key insight is that anomalies are few and different, so they're easier to isolate. The algorithm builds random trees. At each node, it picks a random feature and a random split value. Anomalies need fewer splits to get isolated, so they have shorter path lengths. The anomaly score is the average path length across all trees. Short paths mean anomaly. The contamination parameter tells the algorithm what fraction of your data is anomalous. 0.01 for conservative. 0.05 as a common starting point, 0.10 for aggressive detection. Scikit-Learn also has an auto option. 6 things to remember. 1. Start with k-means. It's fast and intuitive. Always try it first. 2. Evaluate properly. Use silhouette scores plus visual inspection. No single metric is enough. 3. Hierarchical clustering gives you flexibility. No k up front. Dendrograms reveal the full structure. 4. PCA is essential. Reduce noise and enable visualization. 5. Isolation forest works without labeled anomaly examples. Perfect for real-world data. 6. Combine techniques. Use PCA to reduce dimensions, then cluster, then detect anomalies. The pipeline is PCA, clustering, anomaly detection. Here's the code you need. For k-means, import k-means from Scikit-Learn.cluster. Create it with n clusters equals 3. Call fit predict on your data. For silhouette score, import from Scikit-Learn.metrics. Pass your data and labels. For hierarchical clustering, import agglomerative clustering. Same pattern. Set n clusters and fit predict. For PCA, import from Scikit-Learn.decomposition. Set n components to 2 for visualization. Call fit transform. And for isolation forest, import from Scikit-Learn.ensemble. Set contamination to 0.05. Fit predict returns +1 for normal and -1 for anomalies. That's unsupervised learning. From k-means to isolation forest. 5 algorithms. 0 labels. Head to dataforall.dev to practice everything we covered today. Every concept has hands-on exercises waiting for you. Link in the description. If this was useful, hit subscribe. We've got the full machine learning track covering classification, time series, and more. Happy learning and peace.